Okay, folks, for this screencast, I'm going to convert some proximity data from an Arduino to velocity. And so basically, I'm going to take the data stream, which is position in millimeters, I believe, and convert that to millimeters per second by running it through a first order derivative filter. So I have the data in this text file here. I've got the time in this column, and then this is the distance in millimeters. And so basically time is going to be, and then so I imported NumPy, I imported matplotlib, and then I imported the trial data. And so time is the first column, and then distance is the second column, and then I'm going to go ahead and just plot the time with respect to distance, or distance with respect to time. And I'm not going to throw a grid or anything on there just because I want to see what it looks like. Okay, so there's my data. Cool. So everything looks good. We can go ahead and do the first order derivative. So I guess I'll keep this plot in here and say let's take a derivative. So what we need to do is if you look at time, right? What we need to do is we need to grab. Oh, that's a lot of data points. We need to compute delta time dt, which is going to be time of, and we need to start at the second data point and go all the way to the end, and then subtract off the first data point and go all the way to the second to last data point. And so hopefully that will run and not give us an error. And so if we do len of time, that's 554. If we do len of time dt, that's 553. And if we throw a figure down and plot dt and show it, oops, there is the time step. And so I'm not sure why this is longer than the other ones. That's a little curious. Yeah, it was like 0.2. I wonder if I maybe just delete the first data point just so we don't have to deal with that. So let me do this again. So first I'm going to compute the delta time. I'm going to plot the distance. I'm going to throw a figure down. plt.plot just dt. I just want to plot dt. And then there we go. So there's a deprecated warning. Do I have two shows in here or something? I don't know what this means. This is the first time I've gotten this error. But anyway, so here are the time steps here. And so basically if you look, that's curious. Do I have a data point that's 0? Because if you have a 0, it's not going to work. No, it's just 0.1 the whole time. So let's just plot the like blue stars here, so we only see the data points. Yeah, why are they? Oh, I'm sorry. It's 0.1 and 0.11. So the Arduino is basically running at 10 hertz. That's what it seems like. And every now and then it runs at like 9.5 hertz or whatever. Okay, so now let's take it to the derivative. So we have the dt. What we need now is dx. And basically we're going to do the exact same thing. We're going to subtract off the second to last data point, and then from the first to second to last data point. And then basically speed is just going to be dx over dt. And so I guess all of this code I probably need to put down here. That way you can see the speed there. And then we can drop a new figure down, and I'm going to go ahead and label this one because I want to be able to see things. So we're going to see time. So we have to go 0 to -1 because the speed is 1 less than the entire vector. And then I'm going to say, that's fine. Let's see, X label is time, Y label is speed in millimeters per second, and then PLT, throw a grid down. Okay, DT is not defined. DT is right there. Oh. Okay, so figure 3 should be my speed. So there's my speed. So this is what I was worried about. If you notice, there are these really, really huge, like high frequency spikes. And whenever you take a derivative, like you can't just take a derivative. Like if you're taking a derivative of a nice signal, there's really no big deal. But if you're taking a derivative of data, you really need to worry about the all of this like high frequency noise here. Like that's just like no good for taking a derivative. So what we're going to do before we take the derivative is we're going to run the distance through a complementary filter. So I'm going to say distance filtered is distance. Oops, filtered is 0 times distance. And then we're going to say, actually, what I want to do, that's fine. I want to zero everything out, but I want to do distance filtered of 0 is distance of 0. So I'm going to assume that the initial point is correct. And then I'm going to say for d in distance. And I'm going to do, no, I don't want to do that. I'm going to do for counter in range 1 comma len of distance. And I'm going to say distance filtered of counter is equal to 1 minus s times distance filtered of counter minus 1, and that's why I started at 1 instead of 0, because I want to take the previous data point and then take distance and then do s times distance of counter, and then s is going to be, let's try 0.5 for now, and then let's drop a figure down and then do PLT plot time comma distance filtered, and then let's throw a label filtered, label raw, PLT x label is time, PLT y label is what? Oops. Distance in millimeters, throw a grid, throw a legend, okay, and then so there we go. So there's the raw and filtered signal, and you can kind of see I'm doing my best to sort of smooth these out, and I don't think it's smoothed enough. So let's talk about what this S does, right? So if S equals 0, right, it's going to totally filter out the signal. And basically what's going to happen is this whole term is going to go to 0, and distance filtered is just going to equal distance filtered. So it's just going to completely filter out the signal. If S equals 1, this whole term is going to equal 0, and it's basically going to turn off the filter. So in this case, the smaller we make S, the more filtering. So I want a lot of filtering. So I'm going to make it 0.1. And that seems a little over filtered. There's like a significant amount of lag here. I did get rid of all those high frequency spikes, but let me try 0.2 and see if we can at least capture a little bit. I think that looks a lot better. Okay, so now what we're going to do is, when we compute our dx here, instead of doing distance, we're going to do distance. Well, actually, I'm going to leave this so you can kind of see the difference. So I'm going to say dx filtered now is distance filtered of 1 minus distance filtered 0 to minus 1, and then speed filtered is dx over dx filtered over dt. And I'm going to come down here and I'm going to plot, I'm going to just copy this, plot speed filtered, and then throw a label down, filtered, no filter, and then label no filter. And then I guess I need to add a legend, PLT legend. And hopefully that looks a lot better. So yeah, I mean, it's hard to say. Let's get rid of the original signal. So there's my speed. I mean, I'd say that looks pretty good. I mean, it looks like there's this little hop here, but in reality, if this were me, I would stop at 50 seconds. Yeah, there is this weird spike here. But see, that could easily have been like erroneous data. But basically, it's negative. I mean, it's getting smaller and smaller and smaller and smaller. So, I mean, there's some like, I mean, it does look like there are these like, it looks like a staircase, you know? So it does look like that's happening. Now, is that the actual data? Like, is there actually sort of this like sine component, or is that like the data being weird? It's hard to say. But it does look like it's flat, negative, flat, negative, flat, negative. And we're kind of getting that oscillation here. So maybe this is a cart moving on a track. So it's possible there's a little bit of some oscillation on that track there. But at the end of the day, I mean, I think we got it. I mean, I took a derivative, I took a filter, and you can see how if you don't filter it, it looks terrible. Let's over filter the data. So I'm going to do like 0.05. So I'm going to make S really small. So you can see here I've like significantly lagged behind. But you look at my speed, and my speed looks way better. So you can kind of see how you can play games with this, and it's hard to be, you know, when you're filtering data and taking derivatives of data, it's hard to be ethical here. I mean, if you publish this data, like, you need to say that, you know, hey, this was my raw data and I filtered it significantly. So, you know, that's just another lesson there. Anyway, I think I've exhausted my data here, or sorry, my video here. If you have any questions about this code here, you know, post in the comments. I guess I'll post the trial data and the derivative function onto my Python GitHub, so you guys can use it if you need it. And I hope you enjoyed this video, and I'll see you later.